In Montreal, a vital highway crossing collapses with tragic consequences.
There were cars falling into the abyss.
Like boom, down.
A cutting-edge skyscraper threatens to rain shrapnel down onto the city 120 meters below.
Just imagine what that would have done to your head.
A legendary space mission with an engineering catastrophe more than 300,000 kilometers from home.
Houston, we've had a problem.
And in France, an historic village that's literally at breaking point.
Toute ma vie, tout est foutu.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. All structures, no matter how well built, must be regularly monitored to ensure their safety. However, some engineering oversights are only spotted after it's too late to act. Like this disaster on a downtown overpass in Canada.
This catastrophe happened in the blink of an eye.
A perfectly cut piece crashed down onto the cars below.
A concrete construction that hid a deadly flaw.
Unfortunately, this was a disaster just waiting to happen.
A stark reminder that engineers don't always get it right.
This was just one oversight after another, which ended in tragedy.
Montreal is the largest city in Canada's Quebec province. Founded by French settlers in the 1600s, today it's home to more than 4 million people and a hub for commerce and culture. As local journalist Amanda Pfeffer knows well.
Joie de vivre, that is what people come to Montreal for, and it's why people love living in Montreal.
Montreal is a cosmopolitan city with a real European flavour and has all the things you might find in Paris. Great food, fine wine, but like any big city, it also has the curse of ever-increasing traffic.
Montreal is built on an island and fast-growing, which means that the roads and construction causes gridlock on streets all over the city, wherever you may live.
In the 1960s, city planners designed a new road system to help alleviate downtown traffic. A key part of the project was a brand new overpass on Highway 19 that would be one of a kind. The side spans had raking columns with short cantilevers. This allowed the middle span, made of pre-stressed concrete, to be suspended across the road without the need for a central support. Expansion joints above each cantilever would allow the structure to flex under the influence of Montreal's drastic temperature fluctuations. The de la Concorde overpass opened to traffic in 1971 and was hailed as a great engineering success.
57,000 vehicles use the overpass every day, and building it helped ease the city's traffic problems.
Engineers built the bridge to last 70 years. But little did they know the design concealed a deadly weakness.
Vulnerable areas of the bridge were taking a daily pounding.
By the 1980s, the overpass had begun to exhibit visible signs of concrete degradation. After a series of patch-ups, an in-depth inspection was carried out in 1992, during which some damaged concrete was removed. Yet the greatest threat remained undetected. On September the 30th, 2006, drivers using Montreal's Highway 19 noticed that something wasn't quite right with the de la Concorde overpass.
Members of the public have reported seeing cracks and large gaps in the deck support. And one driver apparently even called the police to report seeing a chunk of concrete the size of a suitcase falling to the road below.
An inspector from Transport Quebec called in and said that an inspection needed to take place. That inspection was put forward to the Monday. An advisory went out to media organizations telling motorists to watch out for falling debris. The highway was not closed.
Despite clearing away and loading the fallen pieces of concrete into the back of their pickup, the highway official decided that the bridge presented no immediate threat or danger.
The overpass and the highway underneath remained open until the follow-up assessment could be carried out. Meanwhile, the concrete continued to show signs of rapid deterioration.
Motorists were starting to see the roadway begin to sink into the structure, and a large bump, they could feel the bump on each side.
Suddenly, disaster struck. The southbound section of the overpass collapsed.
A perfectly cut piece of the slab on top had come off and crashed down onto the cars below.
Dr. Claude Giroux was nearby and heard the collapse.
There was a big hole here. Underneath, I saw that truck, and then I saw a car underneath with the whole mass of block and the cement there.
Emergency crews were trying to see whether anybody underneath that concrete was still alive.
Tragically, the catastrophe resulted in 5 fatalities. In the wake of the disaster, the people of Montreal demanded answers. Further investigation revealed that the structure's design was inherently flawed.
The design was considered innovative at the time, but it also meant that it was nearly impossible to carry out a thorough inspection.
It was built to be very difficult to inspect, in fact. You would have to actually drill core samples into the bridge to see if there was rusting or problems with the rebar, that kind of thing.
The overpass's design prevented proper inspection of the abutments and cantilevers, the exact points that carried the full weight of the bridge. It was here that the catastrophic failure occurred.
The De la Concorde overpass effectively collapsed under its own weight in what's known as a shear failure.
A shear failure occurs when a load exceeds the material's shear strength, causing a sliding failure parallel to that load. An inspection showed that the shear strength of the overpass had been compromised at critical points.
Although it happened instantaneously, this catastrophic and tragic failure was a result of years of deterioration.
It seems the engineers who designed the structure underestimated how quickly the points below the expansion joints would degrade.
This error in calculations resulted in a huge amount of stress on the corners of the cantilevers. It essentially created a weak zone that just couldn't handle such a large load.
It was discovered that the rapid degradation at these weak points was caused by the effect of Montreal's climate on the concrete.
It should be no surprise that winters in Montreal can be very harsh, with plenty of snow and ice. Authorities use a lot of salt on the roads to make them safer, but incredibly, engineers hadn't taken that into account when choosing the concrete.
For decades, salty water had been entering the structure around the expansion joints above the cantilevers, into inclusions in the concrete. Seasonal freezing and thawing caused the concrete to crumble at an unpredicted rate. This all culminated in sudden diagonal shear fractures across the cantilevers on both abutments. The result? A total failure of the overpass. Not only that, experts deemed the quality of the concrete used to be substandard, as it lacked sufficient rebar reinforcement at the cantilever abutments. Professor of Structural Engineering Lofty Gisani explains.
It's a shear crack which developed here. It's a diagonal crack, and this is a typical crack. We observe it in beams without steel reinforcement in shear. So this crack has been observed only 30 minutes before the failure of the bridge. And this crack, because of the absence also of the shear strengthening, it can widen quickly and make a brittle failure in shear.
The overpass on Boulevard de la Concorde was built in 1970 and was expected to have a lifespan of around 70 years. But by using poor quality concrete, tests showed that engineers had effectively halved its lifespan.
Now engineers were tasked with fixing this gaping hole. The government inquiry into the de la Concorde catastrophe of 2006 concluded a combination of design choice, substandard materials, and environmental conditions had all contributed to the tragedy. Not only that, but the inspection and restoration in 1992 had significantly compromised the structure.
Not only did the 1992 inspection not fix the problem, but by removing much more concrete than they had planned, it actually made things a whole lot worse.
The current practices for structures that are exposed to freeze-thaw calls for the installation of a waterproof membrane to prevent the infiltration of salt-laden water, which can damage the concrete. But this was never installed, even during the extensive bridge repairs in 1992.
Engineers have argued that the works carried out in '92 should have also included reinforcement of the cantilevers and abutments of the overpass.
According to experts, the shear reinforcements would have strengthened those critical areas of weakness and controlled the internal cracking. And then just maybe this collapse could have been prevented.
The de la Concorde tragedy prompted an inspection of similar structures in the area.
As well as having exactly the same flaws as de la Concorde, the de Blois overpass was in fact built in the same construction project. It was close to traffic less than 3 hours after the collapse and subsequently demolished.
It wasn't just the de Blois overpass that came under the microscope. Multiple bridges across Canada were closely inspected.
I believe there were like 300 inspections that took place after this bridge collapsed. Half of the bridges needed further inspection, and a quarter of them actually needed major repair, as it turned out.
Hundreds of millions of dollars have been invested in the infrastructure, and over 100 overpasses have been closed to all trucks in excess of 20 tons to make sure something like this never happens again.
Today, Canada's Highway Authority remains committed to the safety of all drivers. But the legacy of the de la Concorde catastrophe endures.
There was a real rethinking of what we take for granted, which is that our bridges are safe, that our infrastructure is safe, and that when we drive underneath them, we won't be crushed by them.
Every time I go on a bridge now, I know that bridge can fall. Or if I go underneath a bridge, I just go right through, because that can happen to anybody.
When it comes to groundbreaking engineering, everything from the foundations up has to be built to last. Getting the basics wrong can lead to disaster. Like this statement skyscraper in England, where 14 million tiles were in danger of raining down from nearly 120 meters.
Just imagine what that would have done to your head.
A record-breaking tower that was a huge headache for engineers.
This was meant to be a statement building, but instead, it nearly turned into a public health hazard.
And a show-stopping construction that could become a downtown disaster. Manchester, in northwest England, is considered one of the UK's cultural and industrial powerhouses.
It was right at the heart of the Industrial Revolution, and in the 1950s was a pioneer in the technological revolution. It's a forward-looking city.
In the 1960s, this pioneering city was about to become home to the UK's tallest building, the CIS Tower. Architectural expert Dr. Richard Brooke explains.
The CIS Tower was built in 1962 to house a cooperative insurance society. I wanted a symbol for power and progress and something that really captured their modern and forward-thinking outlook.
For inspiration, architects looked across the pond. where big, bold buildings were in plentiful supply.
The architects went to the US seeking inspiration, and they found it.
It drew on American precedents from Chicago and New York. This was constructed from steel, so it was more akin to its American cousins.
While it would be nowhere near the size and scale of its American counterparts, for the UK, this building was a real high flyer.
At 25 stories high, this would be the UK's tallest building.
The key idea was to improve the office space by removing the services, so elevators, cables, pipes, all that lot, into a separate tower. So you basically have a clean office space with a service tower bolted on the side.
The building had 3 parts: a modest 5-story office block, a much taller 19-story glass-walled office tower, and rising above both would be a 25-story service core. With no windows needed on the service core, designers decided to cover the entire surface with a mosaic made up of 14 million 1¼ centimetre square tiles.
Every statement building needs something to shout about, and 14 million tiny tiles all the way up the service core is one heck of a statement.
The CIS tower was absolutely unprecedented at the time, and the architects were absolutely enthralled by its design quality. But they really wanted this to be a symbol of progress and success.
Opened in 1962, the CIS tower stood tall in this industrial heartland. But shortly after opening, the gloss was literally coming off this brilliant design.
The tiles were meant to shimmer and sparkle. An unexpected turn of events started to take the shine off the building.
Within just 6 months, some of the 14 million tiles were beginning to plummet down to the sidewalk below. And at nearly 120 metres high, toppling tiles in the middle of downtown Manchester, no matter how tiny, had the potential to do some serious damage. As concrete expert George Ballard explains.
You've seen what happens to your windscreen, your windshield, when a stone flies up and you're doing 30 miles an hour, 50 kilometers an hour. It chips the hardened glass. Just imagine what that would have done to your head. These are vicious and dangerous as they fall.
One of those tiles falling from 25 stories could reach speeds of over 100 miles an hour. You would not want to be standing underneath that.
Luckily, there were no recorded injuries, but this groundbreaking facade was in serious danger of losing face. And as tiles on Manchester's CIS Tower continued to fall from the sky, people wanted to know how this groundbreaking building had become a runaway disaster. It turned out this titanic tower was shrinking. George Ballard explains.
With the CIS tower, if we start just with the concrete tower itself, when it's constructed, the concrete itself shrinks as it cures, and it shrinks by about 1 millimetre per metre. And that is over the entire length.
This might not sound like much, but with a 120-metre tall building, as it dries, the concrete can shrink by nearly 18 centimetres.
That happens over a period of 9 months to a year. But the tiles, however, are fixed very early on in its life, and so they're put on and they're put into compression by the shrinking tower.
The tiles were fixed into place very early on in the construction phase, but no one had taken into account concrete shrinkage.
As the concrete dries, it loses excess water, which results in a small reduction in volume known as shrinkage. If something, such as tiles, prevents that natural shrinking process from occurring, cracks can form, damaging the adhesive holding the tiles in place. But that wasn't the only problem.
If I take, for example, the tiles here, they're similar to the ones on the CIS tower. On a cold night, the whole building cools down and it shrinks somewhat. Then the sun comes out, it shines on these tiles, they absorb heat, and they expand. They're trying to push against the building. They try and push very hard, and eventually, if there's any loose tiles, a damaged tile, any of these may cause it to pop off.
Shrinkage is a well-known problem in concrete buildings. It seems an obvious solution had been overlooked.
Normally, in buildings, this is well understood and it's catered for, and every now and then, a movement joint is put in to allow the building to expand and contract. And that would have released a lot of the stress that developed in these tiles.
An expansion or movement joint is designed to hold a structure in place, while safely allowing some expansion and contraction of the building due to shrinkage and changes in temperature. Unfortunately, a lack of expansion joint built into the CIS Service Corps' design significantly contributed to the failure of the multi-million-piece mosaic.
Without expansion joints, the tiles had no room to adapt to the ever-changing weather. They couldn't contract or expand, and so they literally popped off the wall.
By April 2003, the tiles were falling off faster than they could be fixed. And after more than 40 years of a failing facade, it was time for a change. The solution was as radical as the original design. The entire 25-story service core would be resurfaced in the largest solar power project ever undertaken in the UK.
The fix was the largest use of solar panels on a building in Britain. More than 7,000 of them cover the entire service core, absorbing the free Manchester sunlight to generate electricity.
Solar engineer Dr. Daniel Davies explains.
And essentially, this is a sheet of glass. The solar cells are encapsulated behind with a polymer skin and an aluminium frame. So the materials that are exposed to the elements are glass and aluminium, which are widely used in construction. So we connect 4 or 5 panels together. On the co-op tower, I think it was 7, built into a cassette, we called it. And that cassette is lifted onto an aluminium structure fixed onto the outside of the building.
On the 3rd of November 2005, the then Prime Minister of the UK, Tony Blair, switched on the UK's largest solar power tower project.
The tower now generates roughly enough power to make 10 million cups of coffee a year.
And the old mosaic tiles are now safely out of sight and out of engineers' minds.
The remaining mosaic was kept in place behind the new solar panel cladding with a wire mesh, but in all likelihood, it will never see the light of day again.
Despite its initial problems, the CIS Tower remains one of the tallest buildings in Manchester, and still one of its most distinguished. And engineers might have been green with their first mosaic design, but their solution turned out to be even greener.
Engineers turned a massive building blunder into an engineering triumph, and in the process did their bit for the planet.
While the initial failure may have been costly, the new solution is making money while the Manchester sun shines.
Twice, this building was ahead of its time, and finally turned disaster into triumph with true engineering innovation.
And this time, the building and the city is all the better for it. When engineers push the boundaries above and beyond, the results can be groundbreaking. But when the stakes are high, even the tiniest oversight can end in catastrophe. Like this infamous disaster that was out of this world.
Apollo 13 is famous for the explosion halfway to the moon. But what few know is that it was primed to blow long before liftoff.
This oversight came to light at a critical moment.
On Apollo 13, we did things that we shouldn't have done.
Any explosion is scary, but when you're halfway to the moon, there would be no one to come to the rescue.
The shocking engineering truth behind this epic fail.
Houston, we've had a problem.
We made a bomb. We thought we lost him.
Florida, the Sunshine State, with its beaches famed for swimming, surfing and fishing. But there is one beach which is renowned for something very different: NASA's rocket launches. Emre Kelly is a space reporter.
There are typically thousands of people here during a launch. You can look all the way down to Cocoa Beach, probably even see Satellite Beach down there, which is where Buzz Aldrin lives. And you can hang out on the beach all day with your family and friends, and then watch a launch too. These days, a landing.
Yet the space missions wouldn't be possible without the tireless efforts of those thousands of kilometers west in Space City. Tracy Lamb is COO at Space Center Houston.
People love to hear about heroes, and we had so many heroes during that time.
In the 1960s, NASA captured the world's imagination with the Apollo program, an epic endeavor to reach our closest neighbor, the moon.
When I think about truly cutting-edge engineering, NASA's quest to reach the moon is right up there with the best of them.
The people that worked during that era, they had never done something like this before. So they had no recipe book, they had no go-by how to do this or do that. They created all of that during that time frame.
At the time, NASA wasn't the only group of engineers with their sights set on the moon. The Soviet Union had their eyes on the same prize. Alex Stuckey is an investigative reporter.
During the Cold War, the United States got so much funding to go to the moon because it really was like, we have to win this war effort. We have to get to the moon first.
The competition was fierce.
In 1957, the Soviet Union launched the Sputnik satellite, something we had never done, and that really sort of kicked off this race to the moon.
Cy Liebergott worked for NASA during the race to the moon.
We never looked at it as a job, and we were young and we were fearless, and we were ready to go to the moon because we just wanted to beat the Russians. And the reason that we were willing to do all that stuff for the first time ever was because nobody ever told us we couldn't land humans on another planet.
NASA's efforts were famously rewarded in 1969 when they succeeded in putting the first man on the moon.
It's one small step for man, one giant leap for mankind.
The ambitions of the Apollo program didn't end there, with engineering prowess knowing no bounds.
When these crews went to space on Apollo 13, any Apollo mission, they were doing a lot of their work on pen and paper with some really basic computer systems, guidance navigation systems. Today, the iPhone in your pocket is thousands of times more powerful and capable than what they had. And they were manually piloting these spacecraft to the surface of the moon.
In 1970, NASA planned another lunar mission. Apollo 13 was meant to be the third landing on the moon. But by now, events back on Earth had stolen the spotlight.
Budgets weren't tight, but war, Vietnam, there was political strife involved, and some people didn't necessarily think the Apollo program was worth it.
After a successful launch on April the 11th, the crew's journey to the moon was suddenly jeopardized when an engineering catastrophe struck more than 300,000 kilometers from Earth. Cy Liebergott ordered a cryogenic stir of the oxygen tanks, a routine operation that ensured the contents of each tank could be measured accurately.
In zero gravity, we found that the cryogenic material would stratify in layers of different densities, and we would get a fakey reading. Once a day, after the crew woke up, we'd have them stir to cryos. And there were these little 4 switches on the main display console, and they'd flip them up and run them for about a minute, and that's done. No big deal.
In zero gravity, the oxygen would separate into layers that made it hard to know exactly how much was in the tank.
I decided, being a good flight controller, that I wanted more data. I wanted to stir the cryos again, just to make sure I knew where we were.
Without warning, an oxygen tank on the spacecraft exploded.
Here, O2 tank 2 is here, and the explosion shocked this upper shelf, causing the feed valves, fuel cells 3 and 1, to shock closed. And then below here were the 2 hydrogen tanks. And the pressure that created blew the whole side of the spacecraft off.
Houston, we've had a problem. Roger, main B under.
The remarkable series of events that followed allowed the crew to safely return to Earth. But that's only half of the story.
When people talk about Apollo 13, the drama nearly always centers on what happened after the explosion. But what is less well known is that it was inevitable and had actually been set in motion years earlier.
The problem stemmed from the design of one specific part of the spacecraft.
After launch, the Apollo spacecraft had 3 main elements: the moon lander, the command module where the 3 astronauts slept and worked, and the cylindrical service module, which, as well as a rocket motor, carried most of the power and life support systems for the trip out and back.
The service module, the big part connected to the command module, essentially malfunctioned and an oxygen tank ruptured.
The service module comprised of 3 levels containing the vital life support elements for the spacecraft. 2 tanks of liquid oxygen, 2 tanks of liquid hydrogen, along with 3 power cells.
It was a replenishable battery, and it produced electricity and pure drinking water. You can't beat that.
The most essential elements for life support in space are oxygen and hydrogen. Each Apollo mission carried pressurized cylinders of both. Used in different ways, they could provide power for heating or lighting, or air for breathing.
So what had caused this essential life support unit to malfunction? The investigation into Apollo 13 revealed that the oxygen tank that exploded had previously been installed on Apollo 10 back in 1968.
The moon missions were highly experimental throughout, and the technology was constantly being improved.
When repurposing that tank, the thermostatic switches inside were compromised.
Although no one knew it, there was internal damage that paved the way for the explosion on Apollo 13.
This undetected damage turned into a major issue when NASA engineers were preparing the tank for reuse on a later mission.
In space, Apollo 13's electricals were designed to run on 28-volt power, but for testing on Earth, they used 65 volts. Nearly all the components were upgraded to operate on both voltages, but crucially, thermostatic switches in the oxygen tanks were overlooked. When the tank was being flushed, it overheated and the insulation melted on the electrical wiring. That's not good when your tank is holding pure oxygen.
This fail lay hidden, only to be revealed in a dramatic display out in space.
When Sy gave the order to stir the tanks, which was the 3rd time on the mission, the lack of insulation on the wires caused a short circuit, creating a spark. That was all it took to cause the explosion, and the rest is history.
As it turns out, the timing of the explosion proved critical to the survival of Apollo 13's crew.
The failure couldn't have happened at a better time. It was going to happen. And if it hadn't happened when I asked for that extra stir, it might have happened when the crew woke up in the morning. It could have happened and when they powered up the lunar module, using up its valuable consumables. Could have happened when they were down on the ground doing the same thing. And they were dead. They were dead.
The tank exploding exactly when it did was incredibly lucky. Any earlier in the mission and the astronauts would have run out of power or oxygen long before they made it back to Earth. If it had happened later, after the lunar lander had separated, 2 astronauts could have been marooned on the moon with another lost in space.
After Apollo 13's harrowing return to Earth, NASA, along with engineers around the world, learned valuable lessons to make future space exploration safer.
A lot of new technologies came from Apollo.
The microchip wouldn't exist if it weren't for the Apollo program, which is sort of important. Just all kinds of, supercomputing capabilities existed because of Apollo, and that's how we got to the moon.
Although Apollo 13 failed to land on the moon, this unforgettable mission served as a critical lesson for both NASA and humankind. When an engineering oversight reveals itself, the outcome can be sudden and disastrous. However, some fails can result in a catastrophe that takes years to unfold. Like this engineering fail in France that is slowly but surely tearing a community apart.
It's a disaster that's divided a town.
Residents can only watch in despair as their homes crumble around them.
C'est leur maison parce qu'elle était trop endommagée pour pouvoir vivre dedans.
Village life would never be the same.
Toute ma vie, tout est foutu.
Lochviller, in northeast France, dates back hundreds of years. Guillaume Urquhart is a local journalist.
Ici, nous sommes dans le centre-ville de Lorvillers et comme vous pouvez le constater, il y a seulement des habitants qui sont soudés entre eux depuis plusieurs générations, qui vivent ici, qui s'entraident. Et il y a beaucoup d'agriculteurs aussi, c'est une commune rurale, donc les gens cultivent la terre pour leur bétail, mais également pour produire des céréales.
Lochviller is a tiny little town in deep rural France. Traditionally, Lochviller's residents have been farmers, but city dwellers looking for a slower pace of life started moving here in recent years.
As the town's population grew, in the early 2000s, a series of new homes were constructed.
Donc, nous sommes ici dans une rue de Lorvillers avec, vous voyez sur votre droite, des maisons anciennes qui ont pour certaines 200, 300, 400 ans. Et ici à droite, vous avez ce nouveau quartier qui a été construit il y a une dizaine d'années avec de nombreuses constructions de maisons neuves.
In 2008, one Lochviller resident invested in a green form of energy that would tap into the power right beneath their feet.
Donc l'habitant de la maison a décidé de s'équiper d'un forage géothermique pour avoir du chauffage dans sa maison. Donc il a mandaté une société spécialisée dans le creusement du sol pour percer un trou afin de capter l'énergie dans le sol.
Geothermal energy is on the rise. The appeal is clear. It's renewable, unlimited, and unlike fossil fuels, it doesn't pump out greenhouse gases.
Geothermal energy involves the drilling of a borehole deep into the earth. The naturally occurring heat underground can then be tapped and drawn to the surface, providing a free, zero-emission method for heating a home. This form of energy may seem simple and effective, but here, engineers inadvertently created an issue that would very quickly become a nightmare for the entire town. In late 2008, residents of the town of Lochviller started to notice that something wasn't quite right underfoot. Jean-Baptiste Camerer lived here when things began to go wrong.
At the beginning, we noticed that some houses were moving at some cracks. There was something else. The soil, the ground were moving, and we were wondering why and where it was going.
Initially, the cracking in structures was difficult to spot, but as time passed, the damage spread, and before long, local residents' lives were being seriously impacted by the phenomenon.
So this is my garage. This is the place where we first noticed a crack in our house. And now we have it was very small at the beginning, and now we have something huge that goes from one side to the other. As you can imagine, it's very difficult to live in a house like that when you know that it's moving and it may one day fall. You don't want to finish the house because you know that everything is lost. It's very hard from a psychological point of view.
A movement of just a couple of inches might not sound like much, but it's enough to wreak havoc on the structural integrity of a building.
Donc le phénomène des mouvements de terrain de l'Orvillers a une double incidence sur les maisons. Les constructions neuves ont plutôt tendance à pencher, produisant de la gîte, alors que les constructions anciennes, comme on le voit ici dans le reste du village, ont tendance à se fissurer. C'est-à-dire qu'au fur et à mesure des années, des petites fissures s'agrandissent et lézardent complètement les maisons qui menacent ruine aujourd'hui. Pour remédier au phénomène, certaines personnes ont pris des préconisations pour éviter que leur maison ne s'effondre. On voit la maison derrière moi, le propriétaire a dû planter des pylônes en métal pour soutenir les fondations. Il y en a plusieurs qui ont déménagé, effectivement, qui ont quitté leur résidence, leur maison, parce qu'elle était trop endommagée pour pouvoir vivre dedans.
In desperation, the people of Lochviller sought the help of experts to determine why their town was coming apart at the seams. An investigation into the damage revealed that the source of the problem lay under their feet.
The town is built on a mix of anhydrite and clay. Now, anhydrite is a material which, when it comes into contact with water, can swell up to 60% larger than its initial volume.
When engineers drilled the geothermal energy borehole in 2008, they pierced the water table around 60 meters below the ground surface.
Anywhere on Earth, if you drill down deep enough, you're going to hit something known as the water table. This is formed when water trickles down from the surface and settles at a certain level. This level will vary in height from place to place, but it is always there.
The water was released into the anhydrite underneath the town.
Anhydrite is like a baby's diaper. Add water and it will expand.
By drilling into the water table, they exposed the bone-dry anhydrite to an unlimited supply of water. So it simply started swelling up like a sponge.
François Villeret, head of the Department of Industrial Risk Prevention, explains.
Donc l'anhydrite se charge en eau, deux molécules d'eau qui viennent se greffer sur les molécules de sulfate de calcium. Et au moment de cette combinaison chimique, on a un gonflement du matériau de l'ordre de 60% de son volume initial. Et donc, l'eau qui remonte ici vient créer ce phénomène de gonflement sur les anhydrites qui se trouvent dans cet horizon-là, et les anhydrites créent une pression.
This reaction put pressure on the ground from below, causing it to swell upward and move sideways.
The process is slow but constant, and as long as water is present, the anhydrite will continue absorbing it, forcing the ground above to bulge and warp.
It's incredible to think that drilling one small hole could cause all this damage. But that's the power of Mother Nature.
And Lochviller's nightmare is far from over.
The swelling of the anhydrite is relentless. If nothing is done, the cracks will continue to grow.
To save their homes, the people of Lochviller are looking to engineers for help.
The engineers needed to figure out how to separate the water table from the anhydrite layer in the ground.
Finally, a plan has been devised to potentially solve the problem.
Pour éviter que l'eau ne remonte, on va creuser un deuxième forage à côté du forage à l'origine du problème. Et puis on va venir pomper dans ce forage. Et en venant pomper dans le forage, on va créer une dépression. Et donc, l'eau de la nappe ne pourra plus remonter jusqu'à la strate géologique de l'anhydrite. Et ça, c'est la solution qui est à l'étude en ce moment et qu'on pense pouvoir mettre en œuvre avec des premiers travaux en 2020.
You'd never have thought that the best solution would be a second borehole, but it's got to be worth a try. If the engineers can't stop the water rising into the anhydrite layer, then the whole town could face ruin.
Hopefully, in the near future, engineers will be able to stop this catastrophe in its tracks.